Welcome to requirements documentation. So we've already talked about some other model-based requirement specification techniques. Now we're going to be continuing with some formal requirement specification techniques. We're still doing documentation, so this is going to be the final part of the documentation part of requirements engineering. So now we're going to start with formal requirement specification. Within this lecture, we're going to talk about a few types of formal specification techniques, but we are going to stick with or focus our time more with colored Petri nets, a very specific type of formal specification techniques. And we're also going to connect this technique with agent-oriented modeling from our previous lecture. So we're going to try and map agent-oriented modeling to CPN mapping. There are two more models that are part of this lecture series, but we are leaving these two other models for self-studies. These are the 4-variable model and also the software cost reduction techniques. These are going to be added with slide content, which are not going to be a part of these videos. So first we start with colored Petri nets. So why are we focusing on colored Petri nets? The reason is that colored Petri nets are very, very good at modeling concurrency and communication in very complex systems. They combine the concepts from Petri nets and programming languages to have a robust understanding of synchronous events happening in your system. So if you're familiar with Petri nets from other mathematical courses, then you are probably going to be in a good place when it comes to understanding colored Petri nets. Colored Petri nets are, like we said before, a formal method of specification. So what exactly does that mean? It basically means that they are syntactically and mathematically defined. So this gives them a more formal basis of understanding your models for requirements. Another very important point about colored Petri net is that they are executable. Basically what that means is that you can execute various events very similar to how you execute a piece of code in a programming language. Also, another benefit for colored Petri net in particular is that they can be derived from other models such as AOM. So we already had a lot of information about AOM in the previous lecture, and we're also going to be talking about how can we derive colored Petri nets, so a formal method specification, from informal, such as AOM. And CPNs, additionally, and the most important part, allows for easy manual and automatic system verification and evaluation. So we're going to be going into detail on how this entire process happens in preceding segments of this lecture. So as you might recall, we talked about this very specific example of having an automated charging station. You might recall that you had a behavioral interface model of this system. So we talked about various activities like having a charging port reserved when a driver wants to charge an EV, which has some preconditions such as the driver already purchased some energy, the charging point is free, and the EV is ready to charge. And also there are some post conditions for every activity, like the driver has reserved the charging point. And you might recall some other conditions which are basically the same that we have done before. But is this enough for specifying the behavior of your system? Why do we do CPNs if we already have these conditions? A question that you might ask is, how do we know if these conditions are enough for specifying the behavior of your models? Is it possible for us to model these conditions and then simulate specific scenarios? For example, can the system handle 10 EVs and 3 charging stations? Or is it possible for the system to get into like an infinite blocking state such that no EVs can charge and no EVs can stop charging? So you might know in computer science, if you're familiar with very basics of operating systems, that there are many different models for having semaphores and other different things to handle synchronicity between different processes and resources being used in your systems. So it is possible to simulate these kind of situations with colored Petri nets and very specific situations that can allow you to evaluate and verify very specific properties that your system would like to have. So that's a motivation for why we want to use CPNs. So that's why we use CPNs, but what exactly are they? If you look at the very basic mathematical definition, they are directed bipartite graphs. So if you know the definition of them, basically bipartite graphs are graphs where you have two disjoint and independent sets, and basically the vertices of your graph are divided into the left side and the right side. And when you have these two sets, the edges of your graph only connect vertices from one set to the other, but you don't have vertices between two vertices inside of the same set. So as you see in the figure, you have the blue set and the red set, and you only have edges between the left side and the right side, but not within the same set. And connecting this to CPNs, there are exactly two sets in every CPN graph. There are places and transitions. So places we represent in these slide sets as blue and transitions in red. And also importantly, we always make places in these ellipses, and transitions have these rectangles around them. This is the notation that we use for colored Petri nets. And when we talk about the edges of graphs, when it comes to colored Petri nets, we call them arcs and not edges. And essentially the rule and why it's called a bipartite graph is that you only collect places with transitions, but you never have an arc coming from a place to another place. So you can have an arc coming from a place to a transition to another place, but you never have like a transition going to another transition. So now that you know a little bit about what the components of this bipartite graph are, we kind of understand, okay, what exactly happens inside of a colored Petri net. So CPNs simulate the change of state within the system using the exchange of these things called tokens. Tokens are these things that reside within and flow between places through transitions. So as we mentioned before, you can have a place, a transition, and another place. And essentially the tokens reside within the places, but they flow between one place to another through the transitions. But the important part is that tokens never stay in transitions. So tokens are always inside of other places. Let's take a good example. So we know like the core concepts of places, transitions. So this is an actual example of a little colored Petri net simulation. So we know that places can hold tokens, and essentially what a token is similar to the database or the programming concept of a number or something like this. And they're basically instances of color sets. Color sets can be similar to something like a data type from programming languages to make this easier to understand. So as an example, in the figure on the right, you have something called place 1, which is the name of your place. On the bottom right, you can see the name of the color set that is associated with this place. And this specifies that place 1 can only have color sets or tokens which are of type int or integer. And as you can see on the top right of this place, there is this notation that specifies which tokens are currently residing inside of this place. So in this specific example, you see that there is a 1, a dash, and a 10. This essentially signifies that there is one token with the value 10 inside of this place 1. And the plus here, don't confuse this with addition or something like this. In this context, ++ basically is just a notation that is a replacement of a comma. So you can just read this as there is one token of type int of value 10, one of 2, and one of 3. So there's a total of 3 tokens with values 10, 2, and 3 respectively. Now, we also have this concept of variables. So if you see, there is place 1 and transition 2 on the top, and you have this variable a written that's on the inscription of the arc going from place 1 to transition 2. This helps us to distinguish between the tokens while they are in transit. So for example, you may not know when you look at a diagram or define the diagram which token, whether it's 10 or 2 or 3, is flowing between place 1 and place 2. So in order to have like a generalized understanding of, or a generalization of referencing for these tokens, we just use a variable. This is very similar to how you use variables in normal programming languages. What's also important is that you also define the data type, or in this case, color sets of your variables in terms of this very specific syntax which you see on the bottom. So you have variable a of type int, and you also have variable a2 of type int. So you might see on the right side you have the a2 inscription of the arc coming from the other place towards transition 1. So as we said before, markings are what specify the tokens held by a place. So we talked already about what's 10, 2, and 3 that are held by place 1. Arc inscriptions are expressions that can modify the tokens when the transition occurs. For example, when you have place 1 and you have transition 2 going into place 2. If you look at the inscription of the arc going from transition 2 to place 2, you see that there is an a plus 1 in there. Exactly what that means is that when a transition is fired between place 1 and place 2 through transition 2, whatever token is flowing through this transition is incremented by 1. So for example, if 10 was flowing from place 1 to place 2 through transition 2, you would have 11 being held in transition 2. And the token before would be missing from place 1 after this transition has occurred. We also have this concept called guards. If you look at transition 1, there is a comma-separated list of conditions that need to occur in order for this transition to be executable. Essentially, these are like a list of conditions that must be satisfied for a transition. So in this example, transition 1 requires that a, the variable representing the token, must always be even. So you have a modulo 2 is 0. Basically, the remainder when a is divided by 2 must be 0, definition of an even number. But it should not be 2. So not a equals 2 essentially says that any number that is even, but it's not 2. So the only token in this case that can go through transition 1 is 10 because it's even, but it's not 2. But 3 cannot go in because it's odd. 2 cannot go in because it is even, but it is 2. Moving on, so we already talked about transitions and how they take place, but it's important to note exactly when these transitions occurred. A transition is enabled if and only if all its incoming arcs have at least one token, all guard conditions are satisfied, and no place that is connected with an inhibitor arc has any tokens. So we look at the first one, the first condition. So if you look at transition 2, you have place 1, which is an incoming arc with the variable a. We know that at least one token exists in place 1 because there are actually 3 of them. There is 10, there is 2, there is 3, which means that transition 2 can occur because it doesn't really have any guard conditions, unlike transition 1. So on the other hand, transition 3 has a inhibitor arc. So you can see on the right hand side there is an arc with a circle at the end of it. Essentially what this means is that if place 2 has any tokens inside of it, transition 3 will never be fired. This essentially gives you, allows you to have like some kind of customized and more flexibility when you define your transitions to a specific use case. We will look at conditions where this is very, very useful. It's very important to know that at one situation, it's possible that there are many transitions that can be fired, but only one transition is fired at a time. So you cannot have two transitions firing at the same time. It's always one transition after the other. So if in order to know all the different situations that are possible within a colored Petri net model, it's important to also simulate one transition happening before the other and also the other way around. So having all different possibilities simulated is a beneficial thing when you look at the different types of possibilities that can happen in a complex system with actors, different roles happening between these actors, and so on and so forth. So now that we know a little bit about what exactly and how these CPNs work, there's this thing called state space simulations. So essentially, we know that these transitions can occur, but so far we've only looked at transitions occurring and the rules behind these transitions. But there is a way to automatically evaluate all different types of transitions in an automated fashion, and then have a final evaluation of your colored Petri net model. So the basic idea is to compute all the reachable states and all the state changes of the CPN model. What we do is we represent every single state in a directed graph where the nodes represent the states of the entire CPN model and the arcs basically represent the occurring events. So what the benefit of this is basically from a constructed state space, it's possible to verify various aspects of the system. So for example, you might be able to know if it is ever possible to have a deadlock in the system. So we mentioned before that it's possible that an EV system has cars that are charging, cars that are waiting for charging, but in some situation, you can answer the question, is it ever possible that there are cars always charging and never being able to stop charging, or there are some EVs that are waiting for charging that will never be able to charge? You can also evaluate stuff like, is there a possibility of always being able to be able to reach a given state? So for example, if there is a state in which your system always reaches, this is a kind of state which might be not recommended to have within your system. You can also have something like a guaranteed delivery of a given service. So for example, you can always know if there is a specific part of your model that is not reachable. So if you know that there is a particular part of your model that is not reachable, you essentially know that this part of the service might not be delivered. So this is something that you can know. So if certain conditions are satisfied, you know that the service is guaranteed. But these are pros of this system. What are the cons? The cons basically is that there can be like a billion different reachable states of your whole system. So because of this, the state space graph size and the computation time required to create the state space graph increases exponentially. So sometimes it might require that you cut down your model into small independent functional parts and then you compute the state space independently. This is possible and is a valid method of evaluating colored Petri nets. So that is the basics and the theoretical background of colored Petri nets. We are also going to be looking at some practical aspects of this. We are going to be using a software called CPN tools. So you can download or install the software from cpntools.org. And it's basically a tool for editing, simulating, and analyzing colored Petri nets. In the next video, we will show you a little demonstration of how to use CPN tools and also simulate a small program reading from a file and then writing to it. And then we will have a lot of nice discussions, and you'll understand a little bit more about how these flows of tokens occurs and so on.